All right, I will do my best to digitally catch that. Let's see, here we go. All right, can everybody see the screen, I hope?
Yep, looks great.
Excellent. So without further ado, we'll jump right into it. Basically, three main points I want to cover today. An hour is not a lot of time, and really trying to keep the presentation to about 35 or 40 minutes, so we have some time for questions. As this kind of thing is usually more of a conversation than a dogmatic presentation, if you will. Basically, first I'm going to talk about why energy storage is more and more needed to facilitate the further growth of PV. Most of this won't surprise anyone who's been reading the news feeds or walked around Intersolar or any of that. But I do want to distill some of that down to points that are meaningful, for folks that are out there installing. And then we'll spend probably the bulk of our time on the various battery technologies and applications. That's something you don't see a lot in the press. They don't spend a lot of time talking about the pros and cons of various battery types. So spend some time on that, because I think that's probably what a number of you are looking for. And then finally, we'll spend just a couple minutes talking about what you might want to do within your business in order to prepare for what we think is coming down the road. So let's, like I said, first start talking about why PV is going to need energy storage going forward. And energy storage in this context at the residential level is almost exclusively batteries. So that's really what we're talking about. So as most of you are aware, I mean, there's a lot of benefit to grid direct PV, which most of us have been installing for quite some time. AE, of course, as I like to put it, started out in 1979. The first grid tie inverter was invented in 1993, and UL 1741 was rolled out in 1999. So those of you who have been with us for a while remember when this grid tie stuff was kind of newfangled and very dubious, and nowadays that's kind of the bulk of the market, but it's starting to trend back. And I think we all are familiar with the benefits of grid direct PV. You're offsetting fossil fuel power. You're making actually pretty cost-effective energy production, but only during the day. And then you have actually very reliable energy production, but again only during the day. So what energy storage gives you is the ability to actually displace fossil fuel power. And that, as those of you that read a lot about this conversation, the argument from the utility side, and it's a credible argument, is that, well, when you put in these big PV systems, you have to put in a similar amount of backup capacity, if you will, from natural gas in order to deal with the intermittency problem. Well, the other way to deal with intermittency without burning a lot of natural gas is to have some kind of energy storage that can respond quickly, and often is much better for the grid than natural gas because it can respond faster and in a more measured fashion. Of course, that relates to the dispatchability of energy production. If you're putting PV into some kind of battery bank, you can choose when to let that battery bank discharge and when to not let it discharge. So you have effectively a power plant you can turn on or off at will, regardless of when the sun is giving you the energy to charge the batteries. Of course, the big advantage I think for homeowners is all of the solar energy can be consumed on site. So the upshot here is net metering becomes optional. And this is important, as we'll get into, as net metering is increasingly becoming at risk in various markets that are increasingly grid saturated. Another one that I think most people are familiar with, and we certainly have spent a lot of time on in the past, is that with energy storage you can be operational during an outage. So that's the traditional kind of battery backup concept, which I personally spent a lot of time on, and many of you have probably joined me for a workshop or a webinar at some point about that. We'll be doing another one here in a few weeks. I'll be doing one in Austin next week, so if any of you are out in that area, feel free to come join us. And then finally, the main value here is with energy storage, the user has control of their energy production, right? So now you're putting it back in the hands of or at the level of an individual home. That homeowner or some energy manager on his behalf can then say, okay, I'm going to put power back on the grid at these times, or I'm not ever going to put grid power back, or I'm not ever going to take grid power, depending on the financial and environmental goals that this particular homeowner might have. So it really gives a lot more localized control. So getting more specific, and why this is a very attractive thing for us as distributors and installers and folks in the trenches of the solar industry to get involved in. The grid-tied battery market is growing and is expected to continue to grow at about 70% a year through 2017, if not longer. And that's on the back of a number of things. First, the battery technology has gotten cheaper, gotten easier to use. And this isn't just the batteries. I mean, lead-acid batteries, are a 120-year-old technology. There's not a whole lot more you can get out of them cost-wise in terms of scale. But there's a lot of balance of system costs that are coming down, and a lot of labor costs is getting alleviated by clever designs that we'll talk about later. Also, energy storage mitigates or eliminates intermittency issues, as we discussed. And it reduces dependency on net metering. So for those of you familiar with the situation in Hawaii, it's very difficult to connect a net metered system in Hawaii today, especially if you're in a high saturation circuit, which is most of Oahu. And that's been an ongoing challenge. You see a lot of press about it. The upshot is HECO is expected to say, well, you can connect it if it doesn't feed back to the grid. That almost requires energy storage to be feasible. As most of you know, ALEC and others are constantly battering on net metering throughout the country. So far, they haven't really won materially any of those battles, but you are seeing some things that make net metering a little bit less attractive to the homeowner in the sense of fixed or variable fees that they have to pay each month, for grid maintenance or however that's termed. So what energy storage does for us there is it makes us a little more immune to that particular bit of politics. And then finally, I think something a lot of our customers certainly realize is that globally the biggest PV markets are all off-grid. There's still lots of people that are over 1 billion people, as we'll talk about, that are off the grid that need power, and energy storage allows you to do that. And also on the backup side, there's more and more storms. We've seen, Katrina and Sandy, and I mean, name your hurricane, and all of them has done just tremendous amounts of damage. I did a little research not too long ago and found, over the last 2 years, in 2012 and 2013, there were over 14 million businesses and homes without power after these major storms, and some of these guys were without power for weeks. So it's not a problem that doesn't exist, right? I mean, it's out there, and people know about it. Even just this year, there haven't been these huge named storms, but just with your typical weather events, we've already had over 1 million people be without power for significant amounts of time in 2014. So it's not something that only happens with a big storm. You see it in more localized areas constantly. Also would point out, for those of us in Southern California, there's horrible drought right now. We're expecting an El Nino event in the spring. That's going to cause a lot, fires in the fall and winter. We'll have massive mudslides, most likely in the spring. That's going to cause a number of folks in some fairly high net worth areas to be without power for a long time, and I think those guys are trying to realize it. So there's markets out there for this. And then finally, time of use structures. For those of you that aren't familiar with that, basically what that means is you're paying a different dollar per kilowatt hour rate at a different time of the day. So most typically you'll see the rates may be, say, 10 cents a kilowatt hour from 8 in the morning until 4 p.m., and then it's 25 cents a kilowatt hour until 8 p.m., and then it's 10 cents a kilowatt hour the rest of the night. So the rate can change pretty dramatically throughout the day. Now, of course, with energy storage, that allows you to arbitrage that, essentially make sure you're selling during the high time and buying during the low time, as it were. And that's one of the value propositions that's going to be more and more prominent as time of use rates become commonplace in residential rate structures, which, again, California expects to get negotiated next year for a 2016 rate case. So looking again at battery applications, backup applications a bit more, you're really selling comfort and peace of mind. So folks, again, these high net worth homes, thinking eastern San Diego County, places like that where you're kind of out in the woods, there's not a lot of redundant connectivity to the grid. Those guys have a lot of outages and they have a lot of money to deal with it. And then on the other side you have folks with medical devices, oxygen machines, dialysis machines, things like that, where being without those devices for an extended period of time is just not an option. So having backup for that is, those are places where there's a lot of value assigned to backup. And again, with businesses, most of the technology we're talking about is fairly small, but there are very large solutions available. The stuff we've got, could probably handle a convenience store or a small grocery. You get out to, say, data centers and things like that. You're probably looking at containerized energy storage, which we can help with, but that's not our stock and trade. And then, of course, local governments. One of the applications I think is a real winner is getting out there with schools and storm shelters and places where there's going to be an emergency shelter and giving it some kind of backup power. There is occasionally even budget for these things. It's fantastic PR. It's a great way to get your business active in the community, get your name out there as someone that can provide this kind of service. So that's again, schools are the most common. Really, what you need for an emergency shelter is a kitchen and a shower, and that's why it typically tends to be schools. But hotels, other things like that could also be designated emergency shelters. So that's a great one to work on with your local municipality. And then, of course, police, fire, medical services. Police stations, fire stations, hospitals. These guys all have or need some form of backup power, and a PV battery backup can give them a lot of advantages, either alongside of or instead of a fuel generator like a diesel gen set. On the other side of the application, and more emerging, you have these energy storage and management applications. So this is giving homeowners control of their energy. So this is real important, again, in places where net metering is restricted or where there's a time of use rate structure and people want to control when they're using their energy and what they're using it for, to really keep control of their costs is what it's all about. So you see a lot of that on the home side. On business side, it's actually a very similar value proposition, just bigger, because businesses have what are called demand charges. So again, for those of you that haven't done a lot of commercial work, a demand charge is basically a charge for the highest kilowatts of demand that you had over the billing period. So in a month, for example, if you used 50 kilowatts for an hour, you're going to have the same demand charge whether you use 50 kilowatts the whole time. And so what energy storage can do is take that, say you normally operate at 10 kilowatts, base load, and you only run at 50 kilowatts for an hour. Well, having energy storage would allow you to take that 50 kilowatts down to something closer to like 11 or 12 consistently, and keep the demand charges under control. And that's a huge savings for companies that have big demand charges in front of them. And then, of course, your businesses also are a lot more likely to have very complex time of use rate structures and things where you can arbitrage that and make a system pencil. These are going in Hawaii and Southern California today, these kind of systems. It's getting more and more prevalent. And then, of course, governments, utilities, it's really all about overcoming intermittency. So that's demand response with energy storage. That's offering supply or load as needed to the grid. Those tend to be larger scale solutions, but if the markets develop in the direction that it's going, there's likely to be a play for homeowners, at a very small scale, to have some savings by doing things that make the utilities' life a little easier. And then, of course, as we mentioned, off-grid. This hasn't really changed much, but it's certainly getting bigger as the pricing for PV modules and other equipment comes down. As I mentioned, there's over 1 billion people globally that have no electricity. So these rural homes, villagers in developing nations. There's a fairly strong off-grid market, domestically here in the U.S. and also in Canada, and then a huge off-grid market in places like Africa, Latin America, where the grids are just incomplete. And so getting out there to some of these smaller villages that doesn't make sense to spend $4 million to run a power line out there. You can go and for a few tens of thousands give them adequate power with a PV system and energy storage. Then, of course, you have a lot of business off-grid applications, thinking cell towers, stuff like that. And then, of course, remote operations where you're augmenting or replacing diesel gensets. That's a fairly common scenario nowadays. And then, of course, governments and NGOs that have healthcare facilities or schools or orphanages. One of my favorite applications is pumping and purification to provide clean water without having any access to to grid electricity. So that's basically the applications. I'll move a little more into, as I said, the meat of this. We'll cover the battery technologies in not great depth, but enough, I think, to give everyone a bit of understanding about, what are the major technologies out there, what are the various advantages and disadvantages, and and how might they be deployed. So, of course, the old standby. Most of us, I think, are familiar with flooded lead acid. This is about the lowest cost, battery storage available, very high cell capacities available, pretty decent cycle life, plenty of flooded batteries out there that'll give you 2,000 cycles or more, if you're maintaining them properly. Because you can replace the electrolyte, they're not so sensitive to overcharging. Those kinds of things are helpful with these batteries. However, they're really intended to be floated or fully charged at least once or twice a week. So you can't just leave them in a partial state of charge for an extended period of time without really damaging the battery. It'll sulfate. They're not sealed, so flooded batteries, you can't mount them sideways. You can't ship them by air. You have to put them in certain kinds of containment when you install them. Those who have ever dealt with these batteries are very familiar with those limitations. The biggest one, I think, for consumers is you have to maintain these batteries. No one who's not committed to the real off-grid lifestyle, as it were, is going to properly maintain their flooded batteries. It's just something we've learned painfully over the years. So that's the challenge, right? You've got to put water in these things every month or so. You've got to equalize them every now and then. You've got to know when and how to do these things. So it's not like just getting power out of the wall. Also, of course, there's some temperature sensitivity there. They're not real good for vehicular applications. And a little known fact is flooded batteries typically don't reach full capacity for 100 to 150 cycles or more. So you start out with usually on the order of about 10% under what the rated capacity is, and you sort of grow that capacity over time as the battery is worn in, if you will. Related to that, and I think a lot more popular today, are absorbed glass matte valve-regulated lead-acid batteries. And what we mean by valve-regulated, any kind of quote-unquote sealed lead-acid battery is typically valve-regulated. And what that means is there's actually vent valves on the battery that prevent it from blowing up, if you will, or inflating as any hydrogen might be off-gassed. and they're just a little one-way valve. That's really all that valve regulated is referring to. Now, absorbed glass mat, that's chemically the same as a flooded battery, except that your electrolyte, your sulfuric acid, is basically suspended in material that looks a bit like a fiberglass paper towel. So it's just a fiber mesh that your electrolyte is suspended in, and just prevents stratification, so you don't have to equalize these batteries. Very low maintenance. One of the big advantages is very, very low self-discharge. These batteries can be left in float for a long time. That's what they like. AGM batteries are probably the leading choice for backup applications, even over and above lithium-ion for some reasons we'll talk about later. It's a good cost-effective solution, and there's lots of different variations available within these. You'll see the little red batteries here. These are pure lead batteries, and they actually have a cycle life that's just a few hundred cycles, but they will live on the shelf almost indefinitely. You can keep these, once they're fully charged, you can put them on the shelf and just not touch them for up to 18 months, and they'll be totally fine. And you can leave them in float for several years, versus a little more traditional, lead antimony battery, where it has more cycles. These run about 1,800 cycles at 50% depth of discharge, so you can actually use these batteries, but they'll only sit on the shelf for about 6 months before you've got to put some float charge to them. So just give you a sense that there's quite a bit of variation within the AGM space. This is probably the battery market with the most variety of product available. They work pretty well at a reasonably wide temperature range. Everyone's kind of used to these. They work in relatively high power applications compared to, say, a gel or some of the other chemistries out there, which means you can draw a fair bit of current. They're at full capacity, pretty much out of the box. Another thing with not only AGM batteries but also with all lead acid batteries is they're fully recyclable. Something a lot of people don't appreciate about lead acid batteries. They think, oh, lead, that's bad, so on and so forth. But the reality is you can take a lead acid battery and chop it up and smelt it down and recover 95 to 98% of the content, which if you're familiar with recycling virtually anything else, is unheard of. I mean, that's on the order of an aluminum can here. You're recycling all of that lead. You're recycling the plastic casing. You're recycling even some of the stuff that makes up the the glass mat and all that's inside the battery. It's really quite impressive how much of that is recoverable, and the fact that when you get a flooded battery in particular, it's usually almost completely recycled content, which is something none of the newer technologies can really claim, as we'll see. However, these batteries are very sensitive to overcharging because, again, they have that valve regulated component to them. So once that hydrogen escapes, that electrolyte boils off, it's gone. You're not going to get it back, and you're going to have less life in the battery after that. Again, similar to all lead acid chemistries, you can't leave it at a partial state of charge because it'll sulfate. However, there is a lot of research being done and products coming on the market where they're adding carbon to the plates, and that is helping to prevent sulfation. So they're getting much better operation at partial state of charge, much better life. Most of those batteries aren't truly market available yet, but they are coming, and the inherent cost of them is really not significantly more than what's out there today. So it's very promising. And then, of course, you have fairly modest cycle life. Most of these batteries are somewhere between 500 and 2,000 cycles at 50% depth of discharge. That's a pretty common AGM cycle life. And again, there's a lot of work being done combining things like carbon, combining supercapacitor technology that will yield cycle life that's the same or better than any of the advanced chemistries like your lithium-ion and so forth, and much deeper depth of discharge. And so that work again is being done. There's some very promising products that are in sort of test phases right now that we'll see in the next few years. So lead-acid batteries certainly aren't done. You see kind of, these are some common configurations for AGMs. On the left is the Outback integrated battery rack with those front terminal batteries. It's a nice little backup or even off-grid solution, and then a little higher capacity version of that with a self-stacking battery set. And then of course you have gel, which is pretty much similar to AGM. The difference here is your electrolyte is a gel. Like if you've ever taken apart a diaper or something, and there's that kind of desiccant sort of gel stuff in there. That's basically the consistency of these gel batteries. It goes in. It's much like an epoxy. One thing to be careful of with gels is not all manufacturers are the same. So there are certain gels are better than others. We tend to not carry the ones that aren't very good. I'm particularly not a fan of a lot of the Chinese gel batteries just because of the way that they put the gel into the battery isn't so great. But they do offer a couple of advantages to lead acid, or to excuse me, to the AGM battery. They can have a little bit better cycle life, and they work a little better at high temperature than your AGMs do. So just a couple of things there. You typically see these in, again, some off-grid applications, and then a lot of your kind of mobile applications. The gel is a fairly popular type of battery to use. But again, all the same disadvantages to most other lead acid technologies. So moving on from lead acid into some of the more modern ones, and again, nickel metal hydride has been around for quite a while, not 120 years like lead acid, but certainly since the 80s. You see these a lot in hybrid vehicles. So if you drive a Prius, or I have a Nissan hybrid, it's got the same battery pack in it. These nickel metal hydride batteries are kind of the battery of choice for most vehicle manufacturers. Decent energy and power density. It's not as good as lithium ion, but it's getting up there. Very high cycle life, cycle depth. Again, comparable to lithium ion. They're very tolerant of overcharging or undercharging, which again is very helpful in these vehicular applications, and potentially also in certain types of energy management applications. A pretty wide operating temperature range, which is important. They're at least comparable to a lead acid battery. Some manufacturers claim a little bit better high-end and low-end range. Just depends on the particular configuration that you're working with. One of the advantages, in the design sense, is it's a fairly flat voltage. As the battery becomes discharged, that voltage stays relatively fixed. So those of you that are familiar with using lead acid batteries, there's a bit of a drop. A battery at 50% depth of discharge is going to have a slightly lower voltage than the battery that's fully charged versus one that's at 80% depth of discharge. One of the big advantages of nickel metal hydride as opposed to nickel cadmium or lithium ion or some of these other technologies is there really aren't any hazardous materials. It's a pretty straightforward chemistry. It's nickel and hydrogen essentially. Cons, they're fairly expensive. They're about 2 to 3 times the price of lead acid, so it's going to cost a little more to use one of these batteries in a system. Fairly low cell voltage. You have about 1.2 volts per cell versus about 2 to 2.5, which you get for lead acid. A fairly high self-discharge rate. So those of you that have nickel metal hydride batteries in your electronics will notice that even if you don't turn the thing on, you lose charge over time fairly quickly. So these really like to be kind of in a normal cycle operation. They also do have a bit of a memory effect, not nearly as bad as the old NiCad batteries, but you need to fully cycle these about once per month. I mean, take them all the way down and then all the way up. You don't have to do that with lead acid, but you really do need that with most of the nickel chemistries. But the kind of the advantage there is you can recondition these batteries the same way. So if they've got a memory effect that's starting to happen where they're not going to get fully charged or not let you fully discharge them, you can just kind of keep cycling these batteries 3 or 4 times to their extremes, and by doing so, recondition the batteries back to their design point. So lithium-ion, which has been probably getting the most press lately. These batteries, of course, widely used in laptops. Tesla's making them famous, using them in EVs, and lots of handheld devices. I mean, your smartphones, your all kinds of little tools, different stuff are using lithium-ion. It's very sexy and cool. The reason for that is primarily you have very high power and energy density. So you can discharge these batteries at up to 40 times the nominal amp hour capacity. And by comparison, a good AGM battery, you can discharge it up to, say, 3 to 5 times normal amp hour capacity. So it's really a lot of current versus the size and weight and nominal capacity of that battery. And the biggest advantage, of course, is just the size and weight, right? You have 40 watt-hours per pound, whereas your lead-acid battery is more like 6. So that's just really, I think that it's the packaging and the energy density that's the big attraction here. Very high cycle life, a high cycle depth. 3,000 cycles or more. I've heard longer claims, but none that are coming from the battery manufacturer themselves. So I'm always a little bit dubious of those. But yeah, very high cycle depth. I mean, these things can go down 80, 90%. Some of them have claimed almost 100% depth of discharge, and without really hitting the cycle life. We'll talk about that how that happens in a moment. The upshot is, so the downside is, of course, they're very expensive. Most lithium-ion batteries in the market today are 5 to 10 times the price of lead-acid batteries. The price is expected to come down as the various manufacturers scale up and as new technology improvements are introduced, things like that going on. But they remain very expensive today. We sell the valence batteries you see here. I mean, this battery is almost $1,000. So and it's not that big of a battery. A comparable lead-acid battery would be maybe a couple hundred. So you get the sense of kind of where these things are at. You have one of the bigger challenges with lithium-ion, just technically, you have some pretty significant thermal management issues. First of all, it's really difficult to operate these batteries outside of kind of a freezing to hot day weather pattern, right? So if you're getting below freezing, they're probably not going to work. If you get above, say 100 Fahrenheit, there's a chance that you will induce a thermal runaway in the battery, which basically means the battery is going to catch fire. Fortunately, the lithium iron phosphate batteries and the lithium iron manganese batteries and ones like that that have the iron chemistry in them are a bit less prone to the thermal runaway risk. It's still there, but it's much more manageable, and it's not going to burn up if you puncture the battery or something like some of the other chemistries will. So most of what you see on the market today is that lithium iron type of chemistry. That said, the thermal risk is still there. It's still a concern. That's the #1 reason, incidentally, why the nickel metal hydrides continue to be much more popular in the hybrid vehicle space, because they don't absolutely need all the energy density they can get from lithium ion, and they're very, very concerned about the fire risk. So those of you remember the Boeing 787, it was related to that issue. The other part of this is, partly because of the thermal management challenge, and also in order to get the high cycle depth, and just the fact that these are very finicky chemistries, you have to have, with a lithium-ion battery, and to a lesser extent, nickel metal hydride, you have to have a fairly sophisticated battery management system. So every battery system, you're going to have a few $100s that you're going to have to spend on a little computer that basically regulates each cell's charge and discharge. And that's going to add not only cost, it's also going to add some design complexity. Because in some cases, as these applications are fairly new, it may require custom programming that battery management system to do what you want it to do. One of the challenges we've had with the valence batteries, shown here, is virtually every application we have to go back to the manufacturer and get them to approve it, and then basically pre-program the BMS to serve that application. So it does add a lot of complexity to the product, and it's something where if you're not making 1,000 of the same thing, it may not be the best technology to use. The other thing a lot of people don't appreciate about lithium-ion is that they're currently not recyclable, and the lithium is a fairly hazardous waste product. So one thing to watch out for is, even though these batteries are much more expensive typically, the prices don't often include disposal costs. And so whereas your lead-acid battery, you'll actually get a few bucks by giving it to a recycler, your lithium-ion, you're very likely to have to pay to dispose of. So you want to keep that in mind with your application. And then, of course, there are various shipping restrictions that get more or less onerous depending on how large the battery is and kind of what you're doing with it. So packaging has a big play there. So finally, a couple of other chemistries that we want to just mention that are kind of up and coming. Sodium ion is very promising. There was actually a sodium ion battery manufacturer at Intersolar that I spent some time with. It's a very interesting technology. Uses basically carbon and manganese and salt water. So very common, non-toxic materials. So very good from a cost picture. There's nothing in it that's inherently expensive. They're getting already very high cycle life and cycle depth. So they can already claim 3,000 cycles at 90% depth of discharge. So that's comparable to a lithium-ion. It's very durable and abuse tolerant. It has actually a wider temperature range than lead-acid. The cost, like I said, is a little more than lead-acid right now, but by the time these things actually get into production, it'll be comparable to lead-acid. And it'll have similar bulk and weight. I think there's some packaging challenges today that aren't too hard to solve, again, once they get into manufacturing in large quantities. One big challenge with this particular technology is the voltage drops off as the state of charge goes down. So it's a much steeper curve than you have with lead-acid batteries, and you want to be aware of that. So very likely, in order to use sodium-ion batteries, you would have to change the firmware in the battery inverter to use a lower voltage without activating the low voltage disconnect, which is a relatively minor problem, but it is something you want to watch out for with those batteries. And then finally, a lot of you probably heard about flow batteries. These are basically mechanical batteries, if you will, where they're pumping the electrolyte past the membrane. They're fairly complex. Takes a lot of work to put these things together. It's really a solution for utility scale. So most of the applications today are large wind and solar farms, and almost everything out there is a one-off. So that remains the case today. There's really not a lot of reason to develop these for residential scale. Again, because of the complexity, there's more parts that can fail. You have little pumps and things like that that you don't want to have to maintain. So it's probably not going to be all that relevant for us in the residential space. But you will hear more about these as they get deployed in these very large solar farms and systems. They look like little chemical plants, and that's essentially what they are. So good fun with those. And like I said, I don't spend a whole lot of time on them just because, again, they're not likely to be all that relevant to the residential space. A couple notes on differences between inverters, just for those of you that aren't aware. Battery-based inverters versus grid tie. Your battery-based inverters are voltage sourced. That means it's building its own waveform from scratch, whereas your grid tie inverter is essentially applying current to the grid waveform that already exists. So it's doing a little bit less work. The other thing that makes your battery-based inverter do a little more work is that you have a fixed low voltage input. So it's coming from this 48 volt or 24 volt or 12 volt battery versus a typical 300 to 350 to 400 volts off of a PV array. So that's kind of an important one. Another big difference related to that is that your battery-based inverter has nothing to do with the array directly. All of the array is managed by your charge controllers or grid tie inverter if you're using an AC coupled system. It never really sees or cares about the array. It only cares about what's the state of charge of the batteries, whereas your grid tie inverter obviously manages maximum power point tracking for the array. The upshot is you have a little lower efficiency for battery-based inverters. The best ones out there today are around 93, 95%, whereas most of your grid-tie inverters are that and above. And again, that's just a reflection of the fact that that battery-based inverter is doing a lot more work. The other difference people will notice right away is the voltage output options are different. So battery-based inverters is typically 120 or 240 volts out, and that's kind of it. If you want to do three-phase, you're going to have to put three inverters together. Whereas with your grid-tie inverters, for obvious reasons, it's typically 240 AC, or it's some form of three-phase output. So again, just spend the last couple minutes on what you can do to get ready for all the upcoming changes. First, do stuff like this. Get familiar with energy storage systems. Learn how they work with solar. Like I said before, we offer a lot of off-grid and battery backup training material, either by webinars like this or workshops that we do. We're not the only ones. There's plenty of other stuff out there. If you're really interested in getting into this, I highly recommend Outback's certificate training program, and as well as a number of SEI courses that cover energy storage on both off-grid and battery backup scenarios. And really the best thing you can do is start offering battery backup today. It's something you can sell today. It's relatively easy to put together. If you haven't done this before, we can help. But it's a great way to make sure that your team understands how to handle batteries, how to set these systems up. And if you've been doing battery backup for a while, as these fancier and more integrated battery management, energy management solutions become available, you'll be ready to deal with them, and you kind of know what you're working with. As far as kind of how to see things develop, keep a close eye on Hawaii and on Southern California, because Hawaii, as I mentioned, they're expected to really push the non-export systems down there. That's something we're already starting to see. And then, of course, in California, we're expected to see time of use rate structures introduced for 2016, and that's going to change the game a little bit as far as the economics of energy management. Another thing you can do is, if you're going to do nothing else, make sure the grid direct inverters you're using have some path for a retrofit. There's a number of them that explicitly approve use in AC coupled systems. So if you're using, for example, an SMA or an Enphase, they actually say, yeah, you can AC couple these with most battery inverters. I think Enphase prefers the Outback Radian, but not all inverter manufacturers are so keen on that. So that's something you want to find out. Ask the manufacturer. You can ask us in some cases. We typically know if the manufacturer knows. In some cases, the manufacturer hasn't made a decision yet, and we'll just have to see. But you don't want to end up voiding the warranty on that inverter because you've AC coupled it and it's not warranted for that. So that's basically the presentation material that I have. So happy to start running through questions whenever you're ready, huh?
All right, great. Thanks, Paul. We will start off our Q&A session here. We got a lot of good questions coming in, and we'll try to get to as many as we can with the time we have. So we'll just get started here. All right, first question, going back to the TOU rates mentioned in the beginning. Since we already have TOU rates in California, are you suggesting that TOU will become mandatory?
Yes. Basically what's happening is there's a 2015 rate case, or excuse me, a rate case is going to get argued before the CPUC next year. And reading the tea leaves, virtually everyone commenting on it is saying that, look, the utilities are going to push for residential time of use rate structures with really no other option available for the homeowner. So yeah, what I'm referring to is the fact that most people in California will end up on a time of use rate structure by 2016. That's the expectation.
All right, great. The next question we have, what financial modeling programs are available for TOU usage supplied with PV and storage?
If you find me, let me know. I've heard of a number of folks that have kind of developed their own spreadsheet-based models. I don't know of anything you can go online and download or anything like that yet. I'm sure it's all coming. There's plenty of people working on that. But as far as what's publicly available, I don't know of anything you can go and access today. However, if you get the rate structure, it is possible to sit down and come up with a fairly simple model in Excel or something that would give you a good idea.
Okay, perfect. Next question. What is the thinking about PV lead in general? What are the thoughts on recycling?
You mean recycling PV panels or recycling batteries?
I would think batteries.
Okay, so as I mentioned, I mean, the lead-acid batteries are completely recyclable, and most of that is strongly encouraged to mandated by law, depending on where you're at. The battery manufacturers very much want to get that material back because virgin lead's fairly expensive. So what you see, based on discussions with manufacturers, most of your sealed batteries, so your AGMs and your gels, that tends to be produced from virgin material. But your flooded batteries are almost entirely produced from recycled content, and that's they can just because of the way they're built, it's easier for them to have a more flexibility in the alloying, and that's kind of what you see. Now the challenge is with these other battery technologies, as most of you know, you can't just throw a battery in the garbage. You've got to take it to a recycling center, or you've got little AAAs or something. You take them to Best Buy and dump them in the big box by the door. The reason for that is these batteries have hazardous stuff in them that has to get either recycled or properly disposed of, and it will continue to be the case. The challenge is some battery chemistries you just can't recycle yet because there's no technology to do it. And like I said, lithium ion in particular, they're working on that. It just no one's really got a rock solid recycling strategy for lithium ion yet. And I think that's going to come to the fore before too long, right? Someone like the Silicon Valley Toxic Coalition or an organization like that is bound to notice sooner or later and raise the red flag.
Okay, next question. Should a lithium ion be stored fully charged or partially charged?
That's the beauty of the lithium ion. It doesn't really matter much. I generally like batteries to be fully charged when they're stored just because you kind of expect that when you start using them. But the beauty of the lithium ion battery, the reason it's so interesting for EVs is it can live in a partial state of charge indefinitely. That's what that battery management system does for it. So there's no sulfation in the chemistry. I mean, it's really flexible that way. So that's basically the other consideration is unlike lead acid, which if you discharge it at all, you want to recharge it right away. Your lithium ion, you actually want to take 20-30% of the battery's capacity before you charge it back up again. I think as lithium ion doesn't like to be in float. So if you've ever noticed with your laptop battery, if you mostly dock your laptop or plug it in, you'll find that battery dies pretty quickly. Whereas it'll actually last longer if you use your laptop as a laptop and don't plug it in at least once or twice a week when you're draining that battery down, which is just kind of a quirkiness of that chemistry and kind of how you would deploy it.
All right, next question. How do nickel-iron batteries compare to the other battery technologies?
Nickel-iron, I didn't cover it. They're not terribly popular, although I do know some folks that use them in renewable energy applications, things like iron Edison, some of those. They tend to be pretty similar to lead-acid batteries in terms of size and weight, and cost is comparable. I think they're a little more expensive typically. They're a bit heavier, though. So it's a heavier, bulkier battery, but you can get pretty long life out of these things. If they're properly maintained, and if I remember correctly, it's a flooded cell in most cases, so they can last longer than a lead-acid battery. That's really the reason people use them, is because they can get 20 years of off-grid use out of them, and then and some guys are working on ways to make that even longer. It's just not something that's getting a lot of attention because they are so huge, and there's just not a lot of people making them.
Okay. Next question. Do you know of any microinverters that are approved to work with an AC coupled system?
Enphase will work explicitly with Outback, with the Radiant inverter. So if you have an Enphase system, then you can AC couple that with the Radiant inverter. As far as I know, they don't approve it for anyone else's inverter, but they do explicitly approve it for Outback. And there's a Enphase tech note on how to do that. So if you go to their website and search AC coupling, you should be able to find their tech note.
Okay. When do you think the sodium-ion batteries will be available?
As I said, I spent a fair bit of time. I think it was Aquas was the name of the company at Intersolar. They have units that they're basically beta testing today. Commercializing a battery technology is not trivial, and so realistically, given the state of the technology today, I would expect it to take on the order of 3 to 5 years before you see a truly commercialized, ready-to-go system like this. Could be a little sooner if somebody comes and injects a lot of capital into that company, but given the state of things as at least I was able to determine from what I could see, I'm not expecting that to be very commonly available for at least another 3 to 5 years.
Okay. And what grid tie inverters are capable of AC coupling?
Again, explicitly, the Enphase with the Radiant, SMA, they basically invented AC coupling, so they're pretty comfortable with it. Technically, you can AC couple ABB inverters and SolarEdge. However, neither of them say that you can do it. So you run the risk of avoiding the warranty on those inverters. I can't really speak to Keiko. I don't have enough experience with them. Frankly, haven't asked them that question, but I would expect that they'd probably work okay, at least from the technical point of view. The only ones that really don't work technically tend to be your high-frequency inverters. So your old SMA HFUS series, your Fronius IG series, these high-frequency inverters they're very sensitive to fluctuations in the grid, and they shut down at the drop of a hat. So what will happen if you use one of those is it won't be reliable to charge the battery because it won't like the waveform from the battery-based inverter well enough to stay connected to it.
Great. The next question we have, is there a UL-approved lithium-ion battery?
I'm not aware of a listing per se. There probably is one. But yeah, I honestly don't know. I'd have to look it up and see what the listing is and which manufacturers need it. It's listings like that are typically for a system because the cell itself can be used by a number of different manufacturers doing a number of different things, and each one of those integrators, if you will, would need to list their complete system. And I haven't seen a lot of UL listings getting touted for lithium-ion, which isn't to say that there aren't any. I'm sure the laptop batteries and stuff like that are part of a listed system because your laptop has to go through UL and the battery has to be part of that. But I'm not aware of any that are for the individual battery.
Next question. How do you determine the cycle life of the battery bank? Are there charge controllers to use to record this?
So a battery cycle is basically any time you discharge the battery significantly and then recharge it. So that counts as a cycle, whether it's 5% or 25% or 80%. So your cycle depth can be very different. And the way the batteries are rated is they basically assume or test a consistent cycle of typically 50% or 80% depth of discharge, and they repeat that until the battery capacity falls below a threshold. So how you record that in real life, if you have a good data monitoring system, you can get a fairly accurate sense of the cycles the battery's been through. but it's harder to determine the cycle depth. And kind of when you combine all of that, if a battery is rated, for example, 3,000 cycles at 50% depth of discharge, your average cycle when you're using it, if you've designed it well, is probably more like 35 or 40%. So it's going to get more life than that. The idea with the magic number of 3,000 is that's roughly a 10-year battery if you're cycling it once a day to something slightly less than what it's rated for. But yeah, in real life, it's pretty tough to determine your battery life expectancy by the number of cycles it's gone through. You just kind of have to know what your load profile is, know what the cycle profile is, and make some assumptions. What are really going to be your indicators of battery life are things like, cell voltages over time compared to one another, looking at the full charge and discharge, how much of the capacity are you actually able to attain, and seeing that deteriorate over time. It's like saying, when's your car going to break based on the number of miles it's gone? It really depends on a lot of variables.
All right, we have time for just maybe one or two more questions.
Mm-hmm.
Paul, what do you recommend for commercial demand charge reduction?
Something like that, like I said, when I was talking about the advanced lead-acid batteries with the supercapacitors, that's a very interesting technology. You're talking about a big containerized battery system in most cases. That's very interesting for that. People are exploring lithium-ion for it, but frankly, it's just too expensive. And so most of the solutions you see today tend to be either nickel metal hydride or lead acid. I think in the future you're going to see those, those ultra batteries, as they're sometimes called, get used in that application. I think they're perfect for that application. And then I think as lithium-ion gets less expensive, it becomes more viable for that application as well. It's pretty hard to do today because you have to have a lot of energy storage there. And what a lot of folks will do is, they'll do some combination of PV energy storage and then maybe like some kind of generator or cogen, combined heat and power system or something like that.
All right. Well, thanks, everyone. That'll conclude our Q&A session. Looks like we're at the top of the hour. If you do have any other questions that we weren't able to answer, feel free to send them to your sales rep. They can put you in touch with Paul or another member of our technical support team to answer those questions for you. We also have our next webinars coming up are also on technical topics like grid-tied battery backup and off-grid. So check the schedule and sign up for those webinars as well to learn some more information from Paul and his team. Just a couple of quick notes here as we close out. That survey will pop up when you leave the webinar. Please give us your feedback, and I'll send you a copy of the presentation. We want to make these very valuable for you and your teams and not waste your time here. We know it's important. Paul, would you like to close out with any notes?
No, thanks everybody for attending. I actually have another meeting that's starting right now, so I got to get running. But again, email us your questions if you anything we didn't cover to your satisfaction. Obviously, this isn't a full-day workshop, but a webinar, and the intent here is just to give you a nice, broad overview of stuff. So happy to help you further. Just let us know how we can do that, and then we'll be in touch.
All right. Thanks, Paul. Thanks, everyone, for joining. In 2 weeks, we'll have the next topic, grid-tied battery backup systems. So log on to our website and register for that in advance. All right. Thanks, everyone. Have a great weekend.